Cowan. I'm going to approach this problem 1368, minimum cost to make at least one valid path in a grid. This is my very first time approaching this problem. I've had no previous exposure to this problem prior to this very moment. I'm approaching the problem in this manner to kind of give you an opportunity to see kind of authentic, organic intuition in real time, and also to give myself an opportunity to kind of just articulate my points and my thought processing as I go through the problem. Okay, so let's go ahead and take a look at this problem. Just so you know, there's been no submissions, there's no run code. This is first time I've seen this problem. All right, the minimum cost to make at least one valid path in a grid. All right, so you're given an n by n grid. Okay, so not necessarily square grid. Each cell of the grid has a sign pointing to the next cell you should visit if you are currently in this cell. The sign of grid ij can be 1, which means go to the right. 2 means go to the left. Okay, so these integers just represent direction. Don't worry about that right now. Notice that there could be some signs on the cells of the grid that point outside the grid. Yeah, so maybe the direction's like outside of the range of the grid. All right, you start at 0, 0. A valid path in the grid that starts in the upper left corner and ends at the bottom right cell, following the signs of the grid. You can modify the signs in a cell with cost equals 1. Return the minimum cost to make the grid have at least one valid path. Okay, so there's this grid. All right, and I have to follow these arrows, but I'm trying to get here. So if I follow these arrows, obviously I'm not going to be able to get here. So something has to give. So I need to change the direction of one of these arrows so that I can find my way to the solution. This one, if I just follow these arrows, I don't have to change any arrow to get to the destination. Okay, so I think it's pretty intuitive that for this problem, we're going to use Dijkstra's algorithm or uniform cost search to get from the top 0, 0 position to the n-1, n-1 position. So I think the easiest way to look at this problem is to think of it as a graph. So I'm going to redraw this system as a graph, okay? So let's see if I can line it up. So here's that first yellow node. So it's a 4 by 4. Okay. It's really hoping I could get it right, but I did it wrong already. All right. So there's these 16 nodes. Right, we start here. Now, the way that this works is it states that if I modify the cell's value, so the direction I go, it costs 1. And if I don't, then the cost is 0. So what that pretty much means is if I was traveling down this graph, if I go the direction of the arrow, so I'm just copying the values of the arrows for all of these nodes, right, and this goes to nothing. There's 0 cost associated with that. So let me just do that quickly. All right. Okay. So the cost of using these edges, since we're running Dijkstra's, and with Dijkstra's you have weighted edges, right? Weighted edges tell you the cost of using an edge, and getting to a destination will tell you that total cost. So the cost of using all of these edges is 0, right? Because you don't have to change anything in the graph to use these edges. So the price associated with using all these edges is 0. Now, if it states that If you want to modify the sign of a cell, it's going to cost 1. So modifying the sign of a cell is essentially using a different edge than the one that's given, right? If I want to modify this cell to go down, it's going to cost 1. And I can do that for any cell, right? So for any cell, I can add these additional paths, right? And all of these additional paths will have costs it's taking forever associated with 1. Jump in here. Trying to go fast as I can. I'm sorry. I probably forgot some. But all of these new cells that I just created, all these new edges I just created, they all have cost associated with them 1, right? Because these are created directions that are different than the ones that were given. And the cost associated with that is 1, right? Maybe I should have colored these differently, but I think you get the gist of it, right? So when I'm traveling down this link, if I use the given path, and it's fine, I'm using cost 0. But the second I need to change the direction, the cost is 1. So if you understand Dijkstra's, you would know then that the total cost to get to the bottom is just the total cost to reach this node. So this is one of those problems where you need to think about, how am I going to map this to a data structure I know so I can apply an algorithm that's efficient. All right, so what we need to do is take this system here, see if I can make it look, and convert it into this graph, and then run Dijkstra's on it. So that's pretty much the gist of the problem. So let's go ahead and try to get started. All right, min-cot. Okay, so we're given this grid. All right, I'm just trying to think about how we're gonna map this out. So we'll make it a default dict, a list, the graph. And then we'll look at each individual. So mn equals length of grid 0. Okay. So we're going to look at each individual node or each individual vertex in our graph, so each of these cases, and add edges depending on if it's the direction it's going, then that neighbor has an edge weight of 0. If it's in a direction that the system isn't going, that neighbor's going to have a edge weight of 1. So I'm trying to think about how I'm going to do this easily. Okay, so G, so our vertice right now, or let's just do this. So that's your vertice V. No, IJ, V equals IJ. We don't need to do that. What am I doing? Okay, so if so for K and L, so I'm going to look at all possible neighbors in range for KL and so what are my possible neighbors? I can go to the right or that's actually down. I can go to, we'll call this direction, and then we'll figure out. So I can go to the right, go down. Sorry, this all makes sense in a second. I just wanted to think of an easy way of doing this where it's not really confusing. Or messy, I guess. So these are the 4 directions I can go in, right? So I can go down, go up, and go right or go left. Okay. Now, if I go from to I plus 1 and j, I plus 1 and j, that's direction 3. I minus 1 and j, that's direction 4. I to j plus 1, that's direction 2. So then that must be 1, and that's direction 2. So let's just reorder these so it's a little cleaner what we're doing here. Okay. Oh, my computer's starting to get crazy. Okay. So so how do we do the weight? So then the graph at ij, so first thing we got to do is if 0 is less than or equal to k, which is less than m, and 0 is less than or equal to L, which is less than N. So it just has to be within bounds, the direction. We're going to say graph at ij. So at this node, we're going to append this tuple pair, where the first pair is the neighbor, and this part here is the weight. So what's the weight of this neighbor? Well, that depends on if grid at ij equals d. So int. So if it does equal the direction, so not equal, right? So the direction is 1, 2, 3, 4. So this is the direction that we're going. Then this will be false and it'll be 0. If this is not the direction that we're going, this will be true and the answer here will be 1. Okay. So let's go ahead and print the graph and then we'll run on. So this whole part here is more or less, man, it does get pretty crazy. Okay. So does that make sense with this? So the price to go to 0, 1 is 0. The price to go to 1, 0 is 1. All right, from 0, 1, the price to go to 0, 2 is 0. To go to 0, 0 is 1. To go to 1, 1 is 1. Okay, so this just on first glance, it seems like it's right. So this whole part was just kind of taking this initial graph, or this initial grid, and turning it into this graph. And that's essentially what we did here. So now that we did that, we can approach Dijkstra's algorithm. So our source and destination. For our source, we have 0, 0. And for our destination, we have m minus 1, n minus 1. All right, for this, we're going to use a priority queue using the heap queue library. So we're going to need a cost default dict to represent the cost to get to each node. And the cost of source is 0, of course. Okay, PQ equals 0, 0. So while there's a PQ, so now I'm just going to run through Dijkstra's algorithm pretty quickly off the dome. So the weight of u and u equals heap q dot heap pop PQ, party Q. If u equals destination, then we return u. Then we return the cost of u. If WU is greater than the cost of u, so essentially if we've already found a better cost to get to a node, we can discard this and continue. And then we just say for what? For v, a neighbor v, and weight of v, in graph of u if weight of u plus weight of v is less than cost of u, then, or less than cost of v, cost of v equals weight of u plus weight of v, and then heap q dot heap push into priority queue. What are we going to push? We push 0, or no, cost of v, and then v. Yeah, we don't want to print all that out because that's going to give us a... All right, now there's tends to be this weird thing with, and there you go. So that's the solution to this problem. Problem I've never seen before. I think that this is a pretty cool an implementation of Dijkstra's algorithm that I really like, that I've kind of created myself. I really like using default Dix. It's a really, I think, simple approach, especially when you're dealing with grids. It could be nice to just use these tuple pairs as nodes instead of trying to give every grid item like an individual vertice number. But yep, that's pretty much it for my solution. Thank you for watching.